Good morning, everybody. My name is Avishay. I'm a PhD student in CSE, and I present an ongoing project with Eitan Adar from the School of Information and Jamie and Sue from Microsoft Research. This project aims to predict and study the task of predicting scientific impact. The motivation for this task is, well, pretty trivial if you are in academia. If not, then it's interesting for hiring committees that have to determine which faculty to hire, or funding agency that need to determine where to put the money, wanting to maximize the return on investment. So as people and scientists, we like to have numbers to quantify impact, and we have a bunch of metrics to measure the impact of entities in academia. For example, individual papers are often measured, their impact is often measured by the number of citations they attracted. Journals' impact is measured by the journal impact factor designed by Garfield, which is essentially the mean citations to recent publications. And institutions' impact is measured by a bunch of metrics by different rankers, number of prizes, like Nobel Prizes won by faculty in the institution, publications and citations attracted by publications published by the institutions. For authors' impact, we have the H-index, which was introduced by Hirsch in 2005, and I will make use in this slide, in this presentation. So this is a brief description of the H-index. It's essentially the largest H such that at least H papers received H citations. One of the downsides of using citation counts to measure impact is that it takes several years for them to accumulate. For example, we have the PageRank paper, which was well cited 5 years after it was published, but became a true hit as Google became so dominant. And essentially, every metric that relies on citation counts have this delay. Oh, it's impossible to read. Well, whatever, we have this H-index for authors that reflects the impact of their publications so far, but it doesn't take into account recent publications that were published like in this or last year. And this increment in their citation count will lead eventually to the increase in the author's H-index, but we have no way to tell what it's going to look like in a few years. So we try to understand what is the lag, or how much time should we wait in order for citation count to become mature enough so we could count on them to adequately reflect the impact of a paper, and from that the impact of an author or venue or public or institution. So we ran this small experiment where we measured the correlation between the citation count attracted X years after publication with respect to Y years after publication. And we have this plot that summarizes all the correlations between all pairs of years. And we can see that the longer we wait, the higher the correlation becomes. So the citation count after X years becomes more informative. And the Y years, the future horizon we are looking at, the farther we look, it's more difficult to predict. Or in other words, the correlation is lower. And assume we wish to have some ground truth of what's the actual impact of a paper, we can set it to 20 years since the paper was published, as most of the papers don't get any citations after 20 years. And 20 years is a long time, so our data won't support experiments to try to predict this metric. So we prefer to have a proxy that relies on citation counts accumulated after a shorter horizon. And we can derive from this plot a sense of what's a reasonable period of time to accumulate citation counts. So if we look at less than 3 years since publication, the x-axis is less than 3, then we can see the correlation is too low in order to consider it an adequate metric. On the other hand, more than 10 years is obviously sufficient in terms of correlation. It's almost 0.7, but our data still doesn't support that much of a time span. So we settle on 4 years. We have a correlation of 0.5 between the citation count accumulated 4 years after publications and 30 years ahead, which is enough in order to tell whether the paper was impactful. And we will use this 4 years when we discuss and define a proper metric for measuring future impact. So the metric we will use to measure future impact should be motivated. And one motivation is, assuming you are in a hiring committee and you wish to predict the performance of a candidate during his tenureship, you are likely to be interested in the impact of the papers he will publish during this future time period, rather than the overall observed H-index or impact attracted by 2018 or the end of this time period, because this traditional H-index will take into account papers published before the period, which you haven't actually invested in, and will give them more weight compared to recent publications. So this plot illustrates what the future H-index will measure, and the other plot measures what I propose as a metric for future impact. So in this one, we can see the H-index takes into account all papers published up to that point and attributes them the citation count accumulated since the publication up to that point. On the other hand, I propose using only publications published during the period of interest and attribute every publication the citation count accumulated 4 years after it was published. So giving equal weight to every paper, essentially. And I believe that this is a more reasonable approach because it's less biased based on past publications. And when we compare the two metrics, we found the rankings by the two metrics are actually quite different. We have a correlation of 0.4, 0.5, depending on the scientific domain we are looking at. And here we have the top 10 authors in the computer science domain, ranked by the H-index observed by 2008 and the future impact or the impact of publications during the period of interest in our experiment, 2004 to 2008. And we see that the overlap is fairly low. And this supports my argument that the two metrics are different. And when we are trying to predict impact or measuring impact during some period, we should consider only publications in that period and attribute each paper fairly. On the other hand, in venues and also in institutions, as I will show in the next slide, the rankings are more similar to each other. And these are the top venues in all domains, and these are the top institutions in computer science, ranked by H-index observed by 2008 and the impact during 2004 and 2008. So the overlap is fairly high, and the rankings are fairly similar. The correlation is much higher than with authors. So we should keep in mind that change in 2 ranks here means much more than a change in 2 ranks in the author rankings, because the impact of Michigan being ranked 18 or 10 is quite significant. So the task we are looking at is predicting future impact the way I defined it just now, 4 years ahead. And we are trying to find patterns that persist over time. So we are training the model on a snapshot taken in 2000 with the target variable computed over the period of 2000 to 2004, and apply it on a snapshot taken in 2004 with the corresponding target response. The data we are using is the Microsoft Academic Search data that covers 15 domains and have 40 million papers and 20 million authors. For every paper, we have the authors, the abstracts, the citations it received in every year, etc. We focus on the 7 largest domains, namely biology, chemistry, computer science, engineering, medicine, math, and physics. And we found each domain is quite different from the others, not only in terms of volumes. Here we see the number of papers and authors active in 2005, and also the number of venues in each domain. So we see a great variation in terms of size of the domains. We also see differences in dynamics, such as the number of references in every paper and the numbers of authors listed on every paper. And this suggests that we are going to see differences in performance across the domains. So it doesn't tell us, we cannot expect, based on this information, what will the differences look like. The features we used for predicting impact are fairly similar to each entity, to higher level entities. For individual entities, we computed the reputation of entities affiliated with the publication, such as the authors who published the paper, the venue in which it was published, and the affiliation of the authors. And we measured reputation by taking the H-index and the sum citations accumulated by them so far. We also measured the reputation of the references, that is the H-index or the sum of citations, the papers, the references of the paper accumulated by the time of publication, in order to serve as a proxy for the interest of the community in the topic of the paper. For higher level entities, we used observed reputation so far, that is the H-index accumulated so far, and some citations, etc. Also self-citations, and the reputation derived by the venues in which they published in. And we also looked at network-based features derived from the citation and the collaboration network, page rank closeness between us, for example. For every feature, we took two temporal versions, one computed over the infinite window, taking all publications until that snapshot into account, and a sliding window that took only the 1 year, last year worth of publication into account. And this is a brief summary of the results. We see the R squared achieved for every domain, for every entity. And we see that papers and authors are much harder to predict compared to institutions and venues. And also we see a great variation among the different domains. For example, we see that medicine is consistently high in every entity level, and math and physics are fairly low compared to other domains across the different entities. As for predictive features, we found that for papers, the citations of references was the most predictive individual feature. For authors and venues, that was the observed reputation so far, with H-index and some citations being fairly close. And for institutions, that was centrality in that citation network. And we also found that the 1 year window features performed better than the entire infinite window features. So if you wish to replicate such an experiment, use the 1 year worth of data instead of dealing with the entire corpus. We tried to understand what leads to these differences in performance between domains. Why does medicine consistently outperforms math and physics? And we looked at different global properties of each domain, and we found some properties that corresponded to the differences in performance we see. One was the dynamic of the domain, or the mean age of a paper cited in a certain year. So we look at the year 2000, all the citations originated at 2000. What was the age at which they were, of the paper at which they were pointing? And we found that math and physics cited much older papers, so it could suggest the publication cycle is longer and it takes more time for citation count to converge in these domains. Another property we looked at is the distribution of citations. We measured the Gini coefficient over the citations that measures how equal the citations are distributed among the different entities, individual papers or authors, and we found that domains that are easier to predict tend to have less equal distribution, and we are still looking at this direction. It's possible this is an indication of a closed community where the rich cite their own, or a rich club. Another metric similar to this one is the reciprocity, how often how likely you are to cite someone who cited you. So we see that there is a bunch of institutions or authors that tend to cite other from their own community, and this is more apparent in the domains that are easier to predict. So if you belong to this closed community, you're likely to do better. For future work, we are going to keep studying these closed communities in science notion and see if we can quantify it better, measure how closed community prevail in each domain. And we are looking at more features that might make our prediction more accurate, like the gender of the author or tendency to collaborate with other gender within an institution. And also looking at time series analysis, not just taking the 1 year window, but taking snapshots over time of reputation accumulated. And we are also looking into content features, detecting emerging content, emerging topics, and speculating that publications on an emerging topic might do better. And also we are interested in predicting the impact of collaboration. So we know the history of two authors, what is the output of their collaboration is likely to be. And that's it.